So welcome everyone to the final seminar in the Peat Metal series this spring. It's been a really great series and seeing so many of you joining us over the last couple of months, and it's a great way to kind of conclude the series today with a talk from Abbey Marcotte, an early stage researcher from the University of Wageningen in the Netherlands. Abbey did her bachelor's and master's at Kansas State University, working on a range of different things, rivers, soils, and so on, but has moved into kind of the wildfire space through the PhD. And today we'll be talking around kind of some of the work looking at the post-fire impacts in terms of heavy metal mobilisation in one of our key kind of peatland fire locations here in the UK. And I'll stop there and I'll let Abbey kind of talk a lot more about the detail, but I'm sure many of us on the call will be familiar with the kind of the Peak District, South Pennines area, and those international colleagues will find out more about it in Abbey's talk. So I'll hand over to you then, Abbey.
Perfect, thanks. Okay. Share screen. All right, it's there, Gareth.
Just pop it into presentation mode and then it should be good to go.
Okay, and I'll turn on the laser just in case.
Yeah.
Well, thanks, Gareth, for the nice introduction. And just as a pre-warning, I'm a bit under the weather, so I might need to like pause and drink some tea or whatnot. So I apologize in advance. But like Gareth said, I'm going to tell you a little bit about my PhD research about post-wildfire heavy metal mobilisation in this contaminated peatland to the east of Manchester, right near the Peak District. So if you're not familiar with peatlands, they provide quite a lot of ecosystem services. And I would say one of the most like prominent, well-studied services, carbon sequestration, but they also store atmospherically derived pollutants. They offer flood control via surface roughness, and they also help to regulate drinking water quality. However, when there's these perturbations or disturbances, they can become degraded. And the services that I listed on the left sort of become disservices. They sort of make these peatlands not healthy anymore. And that can cause carbon release to the atmosphere, metal pollutant release, erosion, nutrient release, things like that. And so, yeah, one of these sort of burning questions, if you will, is what's going to happen to temperate peatlands or northern peatlands as climate continues to change, because we have more like intense, frequent warming and drought events. And at least in these traditionally non-fire prone regions, the fire frequency and intensity is getting higher and higher, and that can cause peat degradation. And it's sort of this feedback loop where peat degradation can sort of enhance these warming events. And what I am focusing on, as you know from the title of my talk, is this release of legacy pollutants and water quality impacts from these temperate peatlands. Yeah. So if you watched the very first webinar, Gareth already told you that there's a long history of research into contaminated peatlands. And so we know that metals do accumulate in at least these blanket bogs in England, but in other peatland areas. And there's this paper that I really like, I think a lot of people like, about how these peat fires are starting to occur more frequently. We don't really fully understand the risks of metal release. And so there's sort of these three like research needs, these overarching research needs. And then my PhD research mainly focuses on the interactive processes of peat fires, and mainly focusing on hydrological and these biogeochemical responses. So one example of this, I would say, future of fire in Northern Europe and these temperate regions is the Saddleworth Moor fire, or some will say Stalybridge, but in the media it's known as Saddleworth for some reason. So just to be consistent, I will say Saddleworth. And well, as you can see, it's burned quite a large area. And this is sort of the famous photo that they use in the news to show just how severe and intense this fire was. And because of its proximity to Manchester, there was concern about the metal release either into the atmosphere or into the waterways, because a lot of the reservoirs are these key drinking water reservoirs for Manchester and surrounding areas. And just because everybody likes photos, I put a lot of photographs from throughout the burnt area. And while you admire it, I'm going to drink some tea. Just to sort of show you this spatial variation. You can see there's some ferns in this small channel or gully, and ash, charcoal, ash. And I think I'm gonna get myself in trouble with this image. It's Nick, my other supervisor. We said we should debate about this at the end, if it was smoldering or a deep burn into the peat, or if this was already pre-existing degradation. So we can unpack that at the end if you're interested. And then here's one of the other channels. You can see the steeper slopes here. So yeah, to sort of capitalize on this, I wouldn't say once in a lifetime wildfire event, but this sort of shocking, unlike another wildfire event in England, we wanted to study the water quality impacts through this source to sink monitoring of metals. And you'll hear me use source to sink quite a lot in the coming slides, and I'll explain what that means. So basically, we studied ash and peat deposits in the hillslope under the different burn severities, and then dissolution and transport of ash during different rainstorm events into the fluvial system. So, and then the accumulation in the receiving reservoir. So actually, this reservoir here is one where we got a lake sediment core, and you can see this sort of layer of soot and burnt materials on the top. And just to give you an aerial view of the burnt peat catchment and our monitoring areas along this hill slope, there was a burn severity analysis, and a lot of ash and peat samples were obtained to do chemical composition and measure the leaching properties. And then also we measured the ash load in the extreme and the high burn severity areas. And then these sort of this stream right here, we set up a water log to measure a suite of water quality parameters and elements, suspended sediment, and of course discharge. And then this lake, you can't see it, but it's the one I just showed. We got a lake sediment core after the first 2 intense rainstorms, I think. And then sort of to walk you through this a bit more. So we have the hill slope scale where we got our ash and peat samples, and then there was also a large scale handheld X-ray fluorescence survey to get an idea of the metals in the peat deposits after the fire. And then moving to the streams. We have our water quality monitoring station at the outlets, and then these sediment traps. And this is sort of assumed flow paths of either particulates or dissolved materials. And then the lake core here. And just to give you an idea of, these sort of intense runoff events, it was pretty dry right after the fire, but we captured the first rainstorm event. And then I just recently got some more data for this storm event, so I haven't analyzed it yet, but it's coming for the paper. And this was another storm event, so I'll show you, I will go pretty much in order and show you some results that I have so far. So source, basically I'm going to tell you now about the ash and peat metal deposits. This is the normalized burn ratio map that I made using Landsat images. So you can see there's, it was in general moderate to high to extreme burn severity. And on these steeper sloping areas like here, and towards with the gullies and the tributaries of this main stream, it's all quite extreme burn severity. And then I just put the sampling locations again so you can orient yourself. So just to throw some data at you, actually quite a lot of data. The hillslope ash, the ash load of the most extreme burn severity was the highest, and it's quite different than the high burn severity area. You can also see like the extreme burn severity area has quite a high ash load, 13 kilograms per meter squared. And then just to show you some photos so you get an idea of it, it's also was quite spatially variable along these different sampling areas. You can see the pockets of white ash and black ash. All right, so the peat deposits, these were peat samples that were obtained and taken to the lab for analyses. And the left bars are the high burn severity and the right bar is the extreme burn severity. So I personally was a little bit surprised to see that the peat samples that were obtained from the high burn severity had higher metal concentrations compared to the extreme burn severity, but that's for me to figure out as I go deeper into this analysis. And then these dotted lines here are values from a study by Tipping et al., sort of like baseline concentrations reported from the region. And you like most of our metals from our study are quite higher than these like baseline unburned as well, except for lead, just by a little bit. And then these grids are from the handheld XRF, the like portable X-ray fluorescence machine that they obtained over a like 30-meter long transect. And it shows quite a lot more spatial variability within the concentrations of metals, which is actually quite cool. Like for example, over here with the lead, it gets all the way up to more than 2,000 milligrams per kilogram. And then just sort of looking at this qualitatively, these pockets or hotspots seem to emerge. Or if you look over here in the top right corner, sort of this like lack of hotspot, I would say. And I haven't looked in detail at this yet, but I'm assuming that it has something to do with gullies or like sort of these naturally occurring sediment traps in the landscape that can like trap different amounts of particles or peat particles, which may increase or decrease the concentration of metals. But I still need to look into that and sort of geo-reference these onto my my maps. All right, so looking at the ash data that we obtained from a similar area, it sort of follows the same pattern with nickel and lead and copper, where the concentration is higher under these high areas. But then aluminium is much higher in the extreme burn severity. And yeah, I also haven't like picked this apart yet, but my first instinct says, yeah, the reason that the burn severities are differing is maybe the ashes are, or like the fuel is sourced from either vegetation or the soil. Like in general, like aluminium, if there's high aluminium, it sort of can indicate that it's a soil source. And then I don't have to show you any data because the dissolved concentrations of metals were below the limit of detection. So pretty much non-existent, which makes sense because the metals aren't really soluble. All right. So I just told you a lot about metals in the hill slope. And now I'm sort of transitioning into like movement of metals from the hill slope into the fluvial system. In case you were wondering what those weird gray triangles were a few slides ago, they are sediment fences that were installed also on the hill slopes. And I don't have I don't have data from before the first storm event right after the fire, but I do have it from the other storm event. And this is like, so before the third storm event, 14% of what was eroded during the monitoring period, which was more than 1 year, eroded like within the first 2 months under the extreme burn severity areas. And then the high severity was, it was, in terms of amount, it was a lot less, but in the high severity areas, it was still 12% from the monitoring period. And I'm not going to show you any spring data, but actually more soil loss and erosion, even more soil loss and erosion occurred in the spring. But yeah, like I said, I won't be showing that today. And in terms of the the stream where we have our monitoring area at the stream outlet, first I'm going to walk you through these graphs first. So it's aluminium, copper, nickel, and lead. And these are all of our like suspended sediment data that we have from the filters from the water probe. And then the top bar is the first storm event, and then the second bar is the second storm event. So yeah, aluminium, even the x-axes are a bit different. So aluminium had the highest concentration overall, and it's sort of matched when we look at the ash and peat data. And then in general, these concentrations are sort of like consistent amongst each other. And then for the solutes, so the dissolved metals in the stream flow, they were, orders of magnitude lower, of course, which, like I said earlier, is probably because, well, metals aren't incredibly soluble and we didn't see a lot of water soluble fractions from the ash or peat. But one thing that's striking is sort of this temporal difference. Like in the first storm events, there's not really a wide range of solutes. And then in the third storm event, it's quite quite different. So I think this is sort of a function of like the catchment, re-wetting and recovering from the wildfire, and sort of affecting the speed of delivery or transport of these solutes from different areas of the catchment. All right, and then lastly for the sink, so the final destination, if you will, the lake. Just to bring back this picture. So yeah, like I already explained earlier, you can see these are the burn materials on the top of the lake. And then this is actually the the lake core that we obtained. And if you look really closely, you can see this sort of grayish, blackish line. And that's, yeah, basically the charcoal and the ash runoff from the catchment. And so this is the principal component analysis with all of the data from the lake core, and the elements that I focused on in this study are sort of bolded and colored purple. And just in general, copper and lead appeared to be sort of linked with the top of the core. And then aluminium appears to be associated with the loss on ignition, the LOI, and the grain size. And nickel kind of, yeah, it's just out here, maybe a little bit linked with the depth of the lake core. And then here's actually the profile of the lake core and the differing concentrations of the metals. So up here is the top, and then it goes down to 25 centimeters. And we did a dating on the core. So roughly this area is associated with the timing of the wildfire. It was dated to the year 2018, which is when the fire occurred. But of course, there's always a margin of error with these datings. But you can see a pretty obvious increase of copper, nickel, and lead. And then aluminium, yeah, initially I was saying to my collaborators that aluminium was decreasing, but it could be that there's just a different pulse of fire-related material with enriched in aluminium, because it does increase like the rest of the elements a little bit, and then it goes down. So if anyone wants to discuss that, I'm all ears. And then the loss on ignition, or the LOI, and the grain size, in general, they go down as well. And I initially had thought, yeah, this is because the ashes are quite fine, and that might be why the grain size is going down. And the decrease of LOI is often, LOI is often used as a proxy for organic material. So if we're having mostly ash runoff, then this sort of makes sense. And then to sort of close it out and put together some thoughts about these results that I had so far. So coming back to the good old aerial photograph, just to summarize the results from each source, transport, sink. So in general, the ash and the peat from the higher burn severity areas had higher metal concentration compared to the extreme burn severity areas. And then but that's a caveat. The hillslope metal concentrations and the ash load were quite spatially variable. And then moving to the streams and the hillslope erosion. yeah, hillslope erosion was greatest from the areas of extreme burn severity, and then what we measured at the stream outlet, the suspended sediments were quite high in metals, but I did not yet compare this to the drinking water standards to confirm that it was exceptionally high or just a little bit high, but I still think it's quite high. And then the lake core was quite straightforward so far. The metal concentrations generally are peaking at the top of the lake core. And so just some thoughts about what we've looked at today thus far. The wildfire likely enhanced metal concentrations in the peat deposits overall, and like I said, most metals were higher in the higher burn severity areas, but it is really spatially variable, and that's something I want to look into. And this sort of landscape heterogeneity complicates things because of the what were the initial depths of the metals within the peat profile, the vegetation that burned, things like that. And just to sort of end on a hopeful note, even though the metals were quite high, I personally think the risk for water quality might be low in this particular instance. Just because we saw a lot of metals in the high burn severity areas, but it seemed like most of the erosion was coming from the extreme burn severity areas. So maybe the metals in the ash and the peat can sort of aren't as highly mobile with the particulates, but again, that needs to be thought about. And that's it for what I will share with you guys. And if you have any questions, you can email me or Twitter me or find me on Twitter, LinkedIn. And of course, thanks to all the people who helped me in the past and with the fieldwork data collection. Let's discuss, or if you have questions.
Thank you very much, Abbey, for the talk and the overview. Lots of different things, lots of different processes, lots